The title of the lesson is called Terminal Voltage, but I think it's easier if you just look up and I explain to you what we're talking about, okay? What's that a symbol for in a battery? What's that a symbol for in a circuit? Whoops. Okay, it's a battery, all right? Sometimes you'll see that's like stacking batteries in series like we've talked about, but generally I've just been putting one battery in a circuit. And I've been doing something like this. We've had a wire going this way, a wire going this way, and we've said, okay, let's suppose this is a 6-volt battery. And let's suppose I have a resistor right here. And to make the numbers really nice, let's suppose this is a 3-ohm resistor. How big is the current flowing through this 3-ohm resistor? Well, first of all, how many volts are we losing going through this 3-ohm resistor? Say it loud. Yeah, go ahead. 6. And so 2 amps. We always start there, but in real life, actually, batteries have resistance as well, an internal resistor. No battery is perfect. We actually lose a little bit going through the battery. So really what we have is this. A little internal resistance. Because it's tiny, we often label it with a lowercase r instead of an uppercase R. So let's suppose that this battery actually has an internal resistance of 0.5 ohms. We're not going to get 2 amps going through here, and we're not going to get 6 volts going through here. Everything is going to change. Why? Well, what's the total resistance of this circuit? These two are technically in series, yes? And so the total resistance, Donald, is actually 3.5 ohms. Get your calculators out, please. The total current is going to be the 6 volts divided by 3.5, which is going to be a yucky number, sorry. If I go 6 divided by 3.5, instead of 2 amps, how many amps are we actually getting in this circuit? 1.7. Now, here's what else that means. That means I'm no longer getting 6 volts here. I'm getting 3 times 1.7. I'm getting 5.14 volts here. Did I round off properly? Sure. How many volts high is this chairlift, Nick? How many volts high is this chairlift? How many volts am I using in this resistor? Where did the other 0.86 volts go? We're actually losing 0.86 volts going through there. Okay? So even though this battery is labeled at 6 volts, how many volts are we actually getting from it? We call this the terminal voltage, the actual voltage. The 6 volts, it's called the EMF. It's the theoretical voltage. It's the one that's printed on the side of the battery. You never get that. So the other day I brought all of these batteries out and we said they're all 1.5 volts. You'll never get 1.5 volts if any current is flowing. Because as soon as current starts to flow, you lose a little bit going through the battery. But here's the weird part. If you change the resistor, everything changes. So remember the 5.14 and the 0.86? Now, instead of a 3 ohm resistor, I put this battery into something that has a 2.5 ohm resistor. Now, what's the total resistance? 2.5 plus 0.5. Now, what's the total resistance? 3. Now, what's the total current? 6 divided by 3 is 2. Now I'm getting 5 volts here, not 5.14. And now I'm losing 1 volt going through the battery. Still 6 volts. The terminal voltage, 5, that changes depending on what you hook the battery up to. So you always lose a little bit going through the battery. Is that okay, Camille? Let's go to the lesson. Terminal voltage. This is the voltage potential difference between the ends of a battery or cell if you actually measure it in the circuit. The ends or posts of a battery are called terminals. A cell contributes some resistance. So here's a picture of a battery, but in real life, there's a little bit of resistance inside the battery itself as you travel through it. So what we do for our circuit diagram is we either show that, or sometimes you'll even see them draw a little dotted line like that to show you that's the internal resistance. You can stay on the lesson, but in the ultimate review, for example, that I gave you, I can tell you which ones are using terminal resistance, or terminal voltage. Oh, right there. That little 0.5, that's supposed to be inside the battery. That's the internal resistance. And they even used a lowercase r to indicate tiny resistor. Oh, right there. But here, I guess I'm going to assume that this is the terminal voltage, that they've included, when they gave me that 24, they've already included what the voltage little drop going through the battery is. In other words, that 24, that's the 5 that you actually got from here, not the 6 that it's labeled. They've done the math. So I is the current flowing through the cell. In fact, this would be I total. Little r is the internal resistance, and we have a new symbol. It's this curly E. This is the EMF. It's an archaic term. What does archaic mean? Anybody know? You've probably heard the word. Okay. It's left over from old days when we didn't understand things really well. Because EMF, it's an abbrev, and it's an abbrev for electromotive force. It's not a force. It's not measured in newtons. This is back when scientists were just starting to learn about electricity, and they knew something weird was going on, and they said, oh, there must be a force pushing the charges through the circuit. It's a change in voltage. They're flowing downhill. So we no longer say electromotive force. We symbolize it with a capital letter E because that's what the textbooks 150 years ago used, and we haven't changed the notation. This is what's printed on the battery. If you buy, what's a car battery? How many volts? No, that's its EMF. You'll never, if you actually were to hook up a voltmeter when the car is running, you would see, oh, it's not 12 because you're losing a little bit going through the battery. Okay. How many volts were printed on this? Who remembers? That's its EMF, not its terminal voltage. That's its theoretical maximum voltage. It never changes. It's a constant because it's based on the chemical reaction when nothing is running. But as soon as you start to have current going through it, you lose some of your voltage because you need some energy to actually get through the battery itself. Okay? Here's the terminal voltage, V. I use VT or V terminal. So in our ski hill analogy, you know, when you come off the chairlift, you ski down a tiny little hill to get off the chairlift. You lose a tiny bit of height actually riding the chairlift. That's like the little voltage drop going through the battery. Except now my analogy breaks down because the height of that hill varies depending on what other resistors you hook up in the circuit. And in real life, the height of that little bump at the end of the chairlift doesn't change. But right there, that's the voltage drop. How do I find voltage? V equals what times what? This right here is I total times little r. this right here is I total times little r. Sorry, you're still writing that down. And then we'll go to the next page. Example 1 says this. What happens to the cell voltage measured by the voltmeter if we close the switch? Well, if we close the switch, are these two resistors in parallel or in series? So, if we add a resistor in parallel, what happens to R total when you add a resistor in parallel? Increases or decreases? R total decreases. What happens to I total then? It increases. So, what happens to I times little r, that little voltage drop going through the battery? Well, that's I total times little r. If it was I'm going to make up some numbers. If it was 0.2 before, since this got bigger, now it's 0.3 or 0.4. It increased. So what happens to the terminal voltage? Well, let's suppose this is a 12-volt battery, and when this was open, we were getting, let's say, 11.8. We were maybe losing 0.2 volts going through the battery. Now we're losing more because current got bigger. Because we're losing more, now instead of 11.8, when we put our voltmeter on there, 11.65. Therefore, V terminal decreases. Now, why is that? We'll do one more line of work. If we were to write a little equation for the battery, we would say its original voltage was that, 12. But going through the battery, we lose, minus. And then don't write this next bit down. Look up, though. Voltage internally, except how do I write V? V equals what times what? Instead of writing that, I'm going to say we lose I times little, that's not a subscript, I times little r. That's your terminal voltage. So if current goes up, your overall voltage that you have left over to run the battery drops. If current goes down, your overall voltage goes up. What if there's no current? What if you haven't hooked the battery up to anything? Then if you put a voltmeter on it, you will read what's printed on the side. Is that all right? So, example 2 says, find the terminal voltage. This is supposed to be an internal resistor. I didn't do the dotted lines, but I put 2 big dots there to say, hey, that's the poles of the battery. It says, find the terminal voltage. The cell supplies energy to the circuit. So the EMF, the maximum theoretical voltage, is 20. That's what's printed on this battery. How many volts are we actually going to measure? What we mean by the terminal voltage is, what's the voltage drop right there? Well, let's figure it out. How? Label downhill. By the way, sometimes they'll put the terminal voltage above the positive. Sometimes they'll put the terminal voltage below the negative, but they'll smoosh them right close to the battery so you can tell it's part of the battery. That was step 1. Step 2 was find total current. Do you see amps anywhere? No. Step 3 was I know 2 things. Do I know 2 things anywhere? Step 4 is ski. How many volts? 20. How many do I lose here? Don't know. How many do I lose here? Don't know. Ooh, skiing didn't help. You know what? These 2 resistors are in series. I don't think I need to redraw this. I think I can just track this in my head. Sophia, what's the total resistance of this circuit then? 32. What's the total current? Well, that's going to be the total voltage. This T is total. This is why I'm writing term for terminal, because I noticed in my early here, this is a graphic I stole. They use VT. I would always put a term so I know that that's the terminal voltage, not the total voltage. Back to here. It's going to be V total divided by R total. In fact, really, it's going to be the EMF divided by R total. It's going to be 20 divided by 32, which is what? Sorry? It should work out to a nice decimal. 0.625 amps. Okay? Prebner, what does this question want me to find? It wants me to find this minus that. This minus I times little r. Right? It's going to be 20 minus 0.625 times 2. minus 0.625 times 2. 18.75. Call it 18.8, but I'll write the 4 sig figs just so we were really accurate. By the way, how many volts are available for this 30 ohm resistor then? 18.75, not 20. What if I replace this with a different resistor? All of these numbers would change and I would quickly recalculate it. Mr. Duick, why don't they just build better and better and better batteries? Well, there's actually a reason you might want an internal resistor. It's for if you're recharging batteries. Example 3 says, find an expression for the terminal voltage, but this time the cell supplies energy to the circuit. This is what we just did. If you want an expression, I guess V terminal was equal to the theoretical EMF printed on the side minus what you lose going through the battery. I'll come back to that in a second, but yeah, right? Maximum theoretical voltage minus what you lose. Maximum theoretical voltage minus what you lose. I can't remember. Did I actually give you that equation on your formula sheet? No? Oh, I got one here. Hang on. Good. It used to be on the provincial exam, and why would you give them an extra equation for, to me, this is still just a continuation of Kirchhoff's laws. However, we can also, first of all, example 4. I'm getting ahead of myself. Example 4. I like example 4. I like example 4. Example 4 is a nice question. It says this. Find the terminal voltage and the internal resistance. Okay. First thing I'm going to do is label downhill. What's the next thing I try and look for? Who remembers? Total current. Ah! See the 1.5? This question is going to fall apart. I don't know how yet, but trust me, this question is going to fall apart. Sophia, how many amps right here? How many amps right here? How many amps right here? I know 2 things. How many volts do we lose going through here? It's going to be whatever 30 times 1.5 is. 45? What's the EMF? How many volts are printed on the side of our battery, Sophia? Say it again. How many did I use there? How many must I have lost going through there then? Has to be. Oh, how many amps are going through here? Uh-huh. What's the resistance? If V equals I times R, I'm going to use a lowercase r because it's the internal resistance, equals V over I, is that right? 5 divided by 1.5. 3.3 repeating. So the internal resistance, what do they want me to find? They wanted me to find the internal resistance. There it is. And the terminal voltage. What's the terminal voltage? 45. What you want, what you have printed on the side of the battery, minus what you lose going through. So V term equals 45 volts. Put a box around that. And little r equals 3.33 ohms. I'll put a box around that. That internal resistance is really important for rechargeable batteries because that's actually what recharges the battery. Example 5 says this: find the terminal voltage if the cell is being charged. Say, what? Huh? Naomi, how big is this battery? What's its EMF? What's printed on the side? Yeah. How big is the charger? Where's the highest point in this ski hill? Here. Where is downhill then? Downhill is this way. Yes? This way. Oh, we're going backwards through the battery. We are recharging the battery this way. Okay. I see a 5 ohm. I see a 5 ohm. I see a 1 ohm. Naomi, what's our total? Yep. What's the total voltage, not 30? $21, right? Gain 30, lose 9. Gain 30, lose 9, if we just look at the batteries. What's the total current? It's going to be 21 divided by 11, which is what? 1.91? 1.91 or 1.92 if we round off properly? Is it not 91 repeating? Oh, okay, I'm sorry. It's 90 repeating. I was thinking it was 91 repeating. 90 repeating. So 1.91 amps. Okay. How many amps going through this little 1 ohm resistor here then? 1.91 amps, yes? How many volts in this resistor? Well, it's going to be 1.91 times 1. But we're going backwards. If you actually measure the terminal voltage here and here, we gain 1.91 and we gain 9. The terminal voltage here, if you measured the voltage across this battery, is actually 10.91 volts. And it's that extra 1.91 volts. That's what's slowly recharging this battery. How could I get it to recharge faster? Well, I guess I could make this resistor bigger, which would make this number bigger, which would make this number bigger. I have a bigger resistance. I could have this voltage larger and maybe make these resistances smaller. But then the problem is, if I make this resistance really big, when I actually put it into something and drain it, I'll lose so much voltage going out of the battery. Now, instead of having 45 volts left over, I might only have 30 volts left over. So this is why almost all of our batteries, our lithium ion and all that, they take so long to trickle charge. It's because we can't have it both ways. We can get most of our voltage going out if we run it with a small internal resistor. We could recharge it faster with a bigger internal resistor, but then I would lose way more voltage when I put it back into the circuit and started running it again. So right now, and I'm talking about standard batteries, they're coming up with clever workarounds, but right now, for the most part, it's okay, slowly trickle charge to recharge. So, example 5 says, find an expression for the terminal voltage if the cell is being charged. You know what? It's this. Terminal voltage is the EMF, this time plus the little voltage going through the internal resistor. That's what a rechargeable battery does. You could make that R bigger to get a bigger terminal voltage to recharge it faster, but then as soon as you put it back into a circuit, you'll lose more going through the battery. It won't be as good a battery. So in summary, if the cell is supplying energy or current to the circuit, we would say this: terminal voltage is the EMF minus what you lose going through the battery. If we're recharging, the terminal voltage is the EMF plus what you gain going backwards through the battery because you're being forced to buy another chairlift. I am not going to test you on rechargeable batteries. I don't even know if I'm going to quiz you on it. I know there's one in the Ultimate Review somewhere, I think, and there's going to be a couple in the homework. And also because rechargeable batteries kind of dominate your life, so I thought I may as well explain to you why it takes so long to recharge these things. I don't know if you ever wondered, Adam, but it's why. Okay? You've never wondered? No, you haven't wondered anything. Okay. If we wanted to write this as a single equation, I guess you could say this: the terminal voltage is what's printed on the side of the battery plus or minus, depending on whether you're charging or discharging the battery, I times R. This is what they used to give people on the formula sheet, and it always kind of bothered me because this is the first time they've given them a redundant formula that they don't need. You can solve it by skiing with Kirchhoff's laws, I think. Is that all right? There you go. What's your homework? You can try number 1. You can try number 2. Your hint for number 2 is gulp. Draw a little picture. 3 is good. 4 is good. You can skip 5. You can skip 6. 7 is good. Skip 8. 9 is good. 10 is good. 11 is good. You can skip 12. And we're done the unit. You can technically also work on the Ultimate Review, but what I would suggest first is work on the take-home quiz. Right now it's 9:15. It was a short lesson. Can I mark the take-home quiz at, let's say, 10:30? Okay, that's over an hour from now. And then I'll give you take-home quiz number 2, and you'll get some time to work on that in class as well. Okay? Well, you know what? I'll give you take-home quiz number 2 right now as well. So if you finish quiz 1, you can start quiz 2 if you're feeling comfortable and confident about it.